My name is Yangjun Wu and I will present our paper, Vote from the Center, 6th of Pulse Estimation in RGB-D Images by Radial Keypoint Voting. Voting has a long and rich history in computer vision. Ransack and half transformation are two popular voting techniques to localize simple geometries such as line and circle. Many recent machine learning methods are still based on these methods. VoNet used half voting without a codebook to detect 3D objects in point clouds. Despite the general object detection tasks, voting also becomes popular in 6-stop pulse estimation. PVNet and PV3D use different voting quantities to vote for key points and use the key point pairs to estimate the ultimate 6-stop pulse. There are two existing common voting schemes in 6-stop pulse estimation, offset voting and vector voting. PV3D use offset voting. The network learns the offset from the key point to each of the foreground points or object points, whereas PVNet use vector voting, which is a series of unit vector pointing to the key point. These voting schemes require at least 2 dimensions for each vote. This can cause the network harder to converge. We hereby propose a one-dimensional voting quantity called radial voting. It is indeed a simple Euclidean distance from each foreground point to each of the key points. The key point selection strategy was also explored. The most common way was fuzzy point sampling. It samples key points on the surface of the object with a sparse distribution, making sure that key points are far away enough to represent the object. Due to the same reason, further dispersion can potentially be beneficial when we introduce dispersed key points. It is selected based on the object bounding box. The pulse estimation can potentially be more accurate when the estimated voting quantities remain at the same accuracy level. In order to verify that our assumptions on the radial voting and key point dispersion are correct, we conduct some preliminary experiments. We use different voting schemes to vote for key points on the 3 objects chosen from the line model dataset. The voting schemes are estimated by the exact same network structure with the exact same hyperparameters. The average and standard deviation distance from the ground truth location to the estimation are then used to measure the performance of each voting scheme. There is a clear reduction on the error when the voter's dimension reduces. Radial voting with a 1D voter is the most accurate on all 3 objects. We also expand the experiment to test dispersed key points. Everything remains the same, whereas the key points are sampled by FPS and dispersed bounding box. Dispersed key point is less accurate on key point estimation. However, the impact on radial voting is minor. We therefore took a step further and experimented the dispersed key points on Horn's method. We forward key points sampled at different dispersion into the Horn's method and measures the estimate pulse by comparing the transformation error and ADDS matrix. The key points are applied with random noise based on the previous experiment to simulate the estimation of the network. 2 times dispersed key points performs best when estimating pulses even with a minor increase of the simulated noise. Based on radial voting and dispersed key points, we hereby propose our method, RCV pulse. During training, an RGB image is forwarded to the fully convolutional ResNet. The network estimates the semantic mask and radial map simultaneously. Both the semantic mask and radial map are supervised by a simple L1 loss, whereas the background pixels of the radial map are filtered by applying the ground truth semantic mask in order to create a region of interest around the object. At inference, the FCN ResNet took the RGB image as input and estimates the same 2 outputs when being trained, a semantic mask and radial map. The estimated radial map is then applied with the estimated semantic mask and forwarding to the accumulate space where votes are accumulated. The peak of the accumulate space, idle east, the location where maximum votes are, is therefore the estimate key point location. The same procedure repeats 3 times for 3 key points. Then Horn's method is used as the least square fitting algorithm for the rotational and translational matrix estimation. An optional ICP can be applied at the end. We evaluated our method on 3 common 6-stop pulse datasets, YCV video, line mode, and occlusion line mode. We achieved sought-out performance when compared to other recent methods. We were the best on both of the occlusion line mode and YCV video datasets. Our method performs especially accurate on relatively small-scale objects such as the ape in line mode. In conclusion, we propose radial key point voting, which is proved to be more accurate than the 2 existing voting schemes, vector and offset, possibly due to its lower dimension. We propose dispersed key point to further improve the results. Last but not least, we achieved sought-out performance on all 3 datasets tested. Thanks for listening. Please refer to the paper for further details.